Hello, welcome to the video lecture series on digital image processing. Last class we started our discussion on image transformation. Today we are going to continue with the same topic, that is, we will continue with the image transformation topic. So, let us see what we have done in our last lecture. In our introductory lecture on image transformations, we have said the basics of image transformation. We have seen what is meant by an unitary transform. We have also seen what is orthogonal and orthonormal basis vectors. We have seen how an arbitrary one dimensional signal can be represented by series summation of orthogonal basis vectors. And we have also seen how an arbitrary image can be represented by series summation of orthonormal basis images. So, when we talk about the image transformation, basically the image is represented as a series summation of orthonormal basis images. After today's lecture, the students will be able to analyze the computational complexity of image transform operations. They will be able to explain what is meant by a separable unitary transformation. They will also know how separable unitary transforms help to implement fast transformations, and of course, they will be able to write algorithms for fast transforms. So, first let us see that what we have done in the last class. In the last class, we have taken one dimensional sequence of the discrete signal samples, so given in the form u n, where n varies from 0 to some capital N minus 1. So, we have taken initially a one dimensional sequence of discrete samples like this, that is u n, and we have found out what is meant by unitary transformation of this one dimensional discrete sequence. So, by unitary transformation, the unitary transformation of this one dimensional discrete sequence is given by, say, V is equal to A times U, where A is an unitary matrix, and this can be represented expanded in the form V k is equal to, we have A k n U n, where n varies from 0 to capital N minus 1, assuming that we have capital N number of samples in the input discrete sequence. Now, we say that this transformation is an unitary transformation if the matrix A is an unitary matrix. So, what is meant by an unitary matrix? The matrix A will be said to be a unitary matrix if it obeys the relation that A inverse of matrix A will be given by A conjugate transpose. That is, if you take the conjugate of every element of matrix A and then take the transpose of those conjugate elements, then that should be equal to the inverse of matrix A itself. So, this says that A into A conjugate transpose, that should be same as A conjugate transpose A, which will be same as an identity matrix. So, if this relation is true for the matrix A, then we say that A is an unitary matrix and the transformation which is given by this unitary matrix is a unitary transformation. So, using this matrix A, we go for unitary matrix, unitary transformation. Now, once we have this transformation and we get the transformation coefficients, the V k or the transformed vector transformed sequence V, we should be also able to find out that how from this transformation coefficients we get back the original sequence u n. So, this original sequence is obtained by a similar such relation, which is given by u is equal to a, obviously it should be equal to A inverse V, and in our case, since A inverse is same as A conjugate transpose, so this can be written as A conjugate transpose V, and this expression can be expanded as u n is equal to summation V k A conjugate k n, where k varies from 0 to n minus 1. And we have to compute this for all values of n varying from 0 to n minus 1. So, 0 less than or equal to n less than or equal to capital N minus 1. So, by using the unitary transformation, we can get the coefficients, the transformation coefficients, and using the inverse transformation, we can obtain the input sequence, input discrete sequence from the coefficient, from the sequence of coefficients. And this expression says that the input sequence u n is now represented in the form of a series summation of a set of vectors or orthonormal basis vectors. So, this is what we get in case of one dimensional sequence. Now, let us see what will be the case in case of a two dimensional sequence. So, for a two dimensional sequence, so if I go for the case of two dimensional signals, then the same transformation equations will be of the form V k L is equal to, we have to have double summation u m n into A k L m n, where both m and n varies from 0 to capital N minus 1. So, here u m n is the input image, it is a two dimensional image. Again we are transforming this using the unitary matrix A, and in the expanded form the expression can be written like this: V k L is equal to double summation u m n A k L m n, where both m and n varies from 0 to infinity. And this has to be computed for all the values of k and L, where k and L varies from 0 to n minus 1. So, all k and L will be in the range 0 to n minus 1. In the same manner, we can have the inverse transformation, so that we can get the original two dimensional matrix from the transformation coefficient matrix, and this inverse transformation in the expanded form can again be written like this. So, from V k L we have to get back u m n. So, you can write it as u m n again is equal to double summation V k L into A star k L m n, where both k and L will vary in the range 0 to capital N minus 1, and this we have to compute for all values of m and n in the range 0 to capital N minus 1. Where this image transform, that is A K L M N, this is nothing but a set of complete orthonormal discrete basis functions. So, this A K L M N, this is a set of complete orthonormal basis functions, and in our last class we have said what is meant by the complete set of orthonormal basis functions. And in this case, this quantity, the VKL, what we are getting, these are known as transform coefficients. Now, let us see that what will be the computational complexity of these expressions. If you take any of these expressions, say for example, the forward transformation, where we have this particular expression VKL is equal to double summation UMN AKLMN, where m and n vary from 0 to capital N minus 1. That means, both m and n, m will vary from 0 to capital N minus 1, n will also vary from 0 to capital N minus 1. So, to compute this VKL, you find that if I compute this particular expression, for every VKL, the number of complex multiplication and complex addition that has to be performed is of the order of capital N square. Okay. And you remember that this has to be computed for every value of k and l, where k and l vary in the range 0 to capital N minus 1. That is, k is having capital N number of values, l will also have capital N number of values. So, to find out VKL, a single coefficient VKL, we have to have of the order of capital N square number of complex multiplications and additions, and because this has to be computed for every VKL, and we have capital N square number of coefficients, because both k and l vary in the range 0 to capital N minus 1. So, there are capital N square number of coefficients, and for computation of each of the coefficient, we need capital N square number of complex addition and multiplication. So, the total amount of computation that will be needed in this particular case is of the order of capital N to the power 4. Okay. Obviously, this is quite expensive for any of the practical size images, because in practical cases we get images of the size of say 256 by 256 pixels or 512 by 512 pixels, even it can go up to say 1k by 1k number of pixels or 2k by 2k number of pixels and so on. So, if the computational complexity is of the order of capital N to the power 4, where the image is of size n by n, you find that what is the tremendous amount of computation that has to be performed for doing the image transformations using this simple relation. So, what is the way out? We have to think that how we can reduce the computational complexity. Obviously, to reduce the computational complexity, we have to use some mathematical tools, and that is where we have the concept of separable unitary transforms. So, you find that we have the transformation matrix, which is represented by matrix A, or we have represented this as A K L M N, and we say that this is separable if A K L M N can be represented in the form. So, if I can represent this in the form A K M into say B L N, or equivalently I can put it in the form A K M into B L N. So, if this A K L M N can be represented as a product of A K M and B L N, then this is called separable. So, in this case, both A K M, where K varies from 0 to capital N minus 1, and B L N, where L also varies from 0 to capital N minus 1. So, these two sets A K M and B L N, they are nothing but one dimensional complete orthogonal sets of basis vectors. So, both A K M and B L N, they are one dimensional complete orthonormal basis vectors. Now, if I represent this set of orthonormal basis vectors, both A K M and B L N, in the form of matrices, okay, that is, we represent A as A K M as matrix A, and similarly B L N, the set of these orthonormal basis vectors, if we represent in the form of a matrix, then both A and B themselves should be unitary matrices. And we have said that if they are unitary matrices, then A conjugate transpose is equal to A transpose A conjugate, which should be equal to identity matrix. So, if this holds true, in that case we say that the transformation that we are going to have is a separable transformation. And we are going to see next that how this separable transformation helps us to reduce the computational complexity. So, in the original form, we had the computational complexity of the order capital N to the power 4, and we will see that whether this computational complexity can be reduced from from the order capital N to the power 4. Now, in most of the cases, what we do is we assume these two matrices A and B to be same, and that is how these are decided. So, if I take both A and B to be equal to same, then the transformation equations can be written in the form V K L will be double summation A K M U M N A L N. So, you compare this with our earlier expressions, where in the expression we had A K L M N. So, now this A K L M N we are separating into two components, one is A K M, the other one is A L N, and this is possible because the matrix A that we are considering is a separable matrix. So, because this is a separable matrix, we can write V K L in the form of A K M U M N into A L N, where again in this case both M and N will vary from 0 to capital N minus 1. And in matrix form, this equation can be represented as V equal to A U A transpose, where U is the input image of dimension capital N by capital N, and V is the coefficient matrix again of dimension capital N by capital N, and the matrix A is also of dimension capital N by capital N. In the same manner, the inverse transformation, that is what we have got is the coefficient matrix, and by inverse transformation we want to have the original image matrix from the coefficient matrix. So, in the same manner, the inverse transformation can now be written as u m n equal to, again we have to have this double summation a star k m v k l a star l n, where both k and l will vary from 0 to capital N minus 1. So, this is the expression for the inverse transformation, and again as before, this inverse transformation can be represented in the form of a matrix equation, where the matrix equation will look like this: U equal to A conjugate transpose V into A conjugate, and these are called two dimensional separable transformations. So, you find that from our original expressions, we have now brought it to an expression in the form of separable transformations. So, you find that this particular expression, that is V, when we have written this V equal to, sorry, so here we have written V equal to, so if you go back to our previous slide, you find that V equal to A U A transpose. So, if I just write in the form A U A transpose. So, I get the coefficient matrix V from our original image matrix U by using the separable transformations. This same equation we can also represent in the form of V transpose equal to A U transpose. Now, what does this equation mean? You find that here what it says, that if I compute A, the matrix multiplication of A and U, take the transpose of this, then pre-multiply that result with the matrix A itself, then what we are going to get is the transpose of the coefficient matrix V. So, if I analyze this equation, it simply indicates that this two dimensional transformation can be performed by first transforming each column of U with matrix A and then transforming each row of the result to obtain the rows of the coefficient matrix V. So, that is what is meant by this particular expression. So, A into U, what it does is, it transforms each column of the matrix A with of the input image A with the input image U with the matrix A, and this intermediate result you get, you transform each row of this again with matrix A, and that gives you the rows of the transformation matrix or the rows of the coefficient matrix V. And so, if I take the transpose of this final result, what we are going to get is the set of coefficient matrix that we want to have. Now, if I analyze this particular expression, you find that A is a matrix of dimension capital N by capital N. U is also a matrix of the same dimension capital N by capital N. And then from matrix algebra, we know that if I want to multiply two matrices of dimension capital N by capital N, then the complexity or the number of additions and multiplications that we have to do is of order capital N cube. So, here to perform this first multiplication, we have to have of order n cube number of multiplications and additions. the resultant matrix is also of dimension capital N by capital N, and the second matrix multiplication that we want to perform, that is A with A U transpose, this will also need of order n cube number of multiplications and additions. So, the total number of addition and multiplication that we have to perform when I implement this as a separable transformation is nothing but of order 2n cube. And you compare this with our original configuration when we had seen that the number of addition and multiplication that has to be done is of order n to the power 4. So, what we have obtained in this particular case is the reduction of computational complexity by a factor of capital N. So, this simply indicates that if the transformation is done in the form of a separable transformation, then it is possible, and as we have seen, that we can reduce the computational complexity of implementation of the transformation operation. Obviously, the final result that we get, that is the coefficient matrix, is same as the coefficient matrix that you get when you implement this as a non-separable transformation. So, advantage that you get by implementing this as a separable transformation is reduction in computational complexity. Now, let us see that what is meant by the basis images. So, what is meant by basis image? Now, here we assume that suppose A k star, this denote the kth column of the matrix A conjugate transpose. So, A k star, we represent this the kth column of A conjugate transpose, where A is the transformation matrix. And now, if I define the matrices A k L star as A k star into A L star transpose. So, you find that A k star is the kth column of the matrix A star transpose. A L star is also the lth column of the matrix A conjugate transpose. So, if I take the product of A k star and A L star transpose, then I get the matrix, a matrix A k L star. Okay. And let us also define the inner product of say 2 n by n matrices. So, I define inner product of 2 n by n matrices, say F and G. So, the inner product of these two matrices F and G are defined as F m n G star m n, where both m and n vary from 0 to capital N minus 1. So, we define the inner product of two matrices F and G in the form of F m n G star m n, where both m and n vary from 0 to capital N minus 1. So, now by using these two definitions, now if I rewrite our transformation equations. So, now we can write the transformation equations as V k L is equal to, you find that the old expression that we have written U m n A k L m n, where both m and n vary from 0 to capital N minus 1. So, this is nothing but as per our definition. So, if you just look at this definition, this is nothing but an expression of an inner product. So, this was the expression of the inner product. So, this transformation equation is nothing but an expression of an inner product, and this inner product is the inner product of the image matrix U with the transformation matrix A star K L. Similarly, if I write the inverse transformation U M n, which is given as again in the form of double summation V K L into A star K L M n, where K L vary from 0 to capital N minus 1. So, again you find that in the matrix form, this will be written as U equal to summation V K L into A star K L, where both K and L vary from 0 to capital N minus 1. So, if you look at this particular expression, you find that our original image matrix now is represented by a linear combination of n square matrices A star K L, because both K and L vary from 0 to capital N minus 1. So, I have n square such matrices A K L. And by looking at this expression, you find that our original image matrix U is now represented by a linear combination of n square matrices A star K L, where each of these n square matrices are of dimension capital N by capital N. And these matrices A star K L are known as the basis images. So, this particular derivation simply says that the purpose of image transformation is to represent an input image in the form of linear combination of a set of basis images. Now, to look at how these basis images look like, to see how these basis images look like, let us see some of the images. So, here you find that we have shown two images. We will see later that these are the basis images of dimension 8 by 8. So, here we have shown basis images of dimension 8 by 8, and there are total 8 into 8, that is 64 basis images. We will see later that in case of discrete Fourier transformation, we get two components, one is the real component, other one is the imaginary component. So, accordingly, we have to have two basis images, one corresponds to the real component, the other one corresponds to the imaginary component. Similarly, this is another basis image which corresponds to the discrete cosine transformation. So, again here I have shown the basis images of size n by 8 by 8. Of course, the image is quite expanded, and again we have 8 into 8, that is 64 number of images. So, here you find that a row of this represents the index k and the column indicates the index L. So, again we have 64 images. Each of these 64 images is of size 8 by 8 pixels. Similarly, we have the basis images for other transformations like Walsh transform, Hadamard transform, and so on. So, once we look at the basis images, so the purpose of showing these basis images is that, as we said, that the basic purpose purpose of image transformation is to represent an input image as linear combination of a set of basis images. And when we take this linear combination, each of these basis images will be weighted by the corresponding coefficient, the transformation coefficient VKL that we compute after the transformation. And as we have said that this VKL is nothing but the inner product of KLth basis image. So, when you compute this VKL, as we have seen earlier, so if you just look at this VKL, which is represented as inner product of the input image U and the KLth basis image A star KL. So, each of these coefficients VKL is actually represented as the inner product of the input image U with the KLth basis image AKL star. And because this is the inner product of the input image U and the KLth basis image AKL star, this is also called the projection of the input image on the KLth basis image. So, this is also called the projection of the input image U onto the KLth basis image AKL star. Okay. And this also shows that any n by n image, any image input image of size, any input image U of size capital N by capital N can be expanded using a complete set of n square basis images. So, that is the basic purpose of our input of the image transformation. Now, let us take an example. So, let us consider an example of this transformation. So, we have been given a transformation matrix which is given by A equal to 1 upon root 2, 1, 1, 1, minus 1, and we have the input image matrix U equal to 1, 2, 3, 4. And in this example, we will try to see that how this input image U can be transformed with this transform matrix A, and the transformation coefficients that you get, if I take the inverse transformation of that, we should be able to get back our original input image U. So, given this, the transformed image we can compute the transformed image like this. The transformation matrix V will be given by 1 upon 2 into 1, 1, 1 minus 1 into our input image 1, 2, 3, 4. So, if you just see our expressions, you find that our expression was something like this. When we computed V, we had computed V equal to A U A transpose. Okay. So, by using that, we have A U then A transpose, and by nature of this transformation matrix A, you find that A transpose is nothing but same as A. So, you will have 1, 1, 1, minus 1. And if you do this matrix computation, it will simply come out to be 1 upon 2 into 4, 6, minus 2, minus 2 into 1, 1, 1 minus 1, and on completion of this matrix multiplication, the final coefficient matrix V will come out to be 5 minus 1 minus 2 0. So, I get the coefficient matrix V as 5 minus 1 minus 2 0. Okay. Now, let us see that what is the, for this particular transformation, what will be the corresponding basis images. Now, when we defined the basis images, you remember that we have said that we have assumed A k star to be the kth column. This was the kth column of matrix A star transpose. Okay. Now, using the same concept, and from this our basis functions was taken as A k L star, which was given by A k star multiplied with A k L star, the kth basis image was computed as A k star multiplied with A L star transpose. So, this is how we had computed the basis images, we have defined the basis images. So, using the same concept, in this particular example where we have the transformation matrix A is given as 1 upon root 2 1 1 1 minus 1, I can compute the basis images as A 0 0 star. The 0th basis image will be simply half into the basis vectors 1 1 and 1 1 transpose. So, this will be nothing but half into 1 1 1 1. Similarly, we can also compute A 0 1, that is 0 1th basis image will be given as half into 1 1 minus 1 minus 1, which will be same as A 1 0, that is 1 0th basis image, and similarly we can also compute A 1 1, that is 1 1th basis image will come out to be half into 1 minus 1 minus 1 minus 1. So, this is simply by the matrix multiplication operations, we can compute these basis images from the rows of from the columns of A conjugate transpose. Now, to see that what will be the result of inverse transformation, you remember the transformation coefficient matrix V we had obtained as 5 minus 1 minus 2 and 0. So, this was our coefficient matrix. By inverse transformation, what we get is our inverse transformation is A conjugate transpose V A conjugate, which by replacing these values will get as half into 1 1 1 minus 1, then 5 minus 1 minus 2 0, and again 1 1 1 minus 1. And if you compute this matrix multiplication, the result will be 1 2 3 4, which is nothing but our original image matrix U. So, here again you find that by the inverse transformation we get back our original image U, and we have also found that what are the basis images, the 4 basis images A star 0 0, A star 0 1, A star 1 0 and A star 1 1 for this particular transformation matrix A, which has to be operated on the image matrix U. And we have also seen that by the inverse transformation we can get back the original image matrix U. Now, let us look further in this separable transformations. So, what we had in our case is we had U as the original image matrix, and after transformation we get V as the coefficient matrix. And you remember that both these matrices are of dimension capital N by capital N. Now, what we do is, for both these matrices U and V, we represent them in the form of vectors by row ordering. That is, we concatenate one row after another. So, by this row ordering, what we are doing is, we are transforming this matrix of dimension capital N by capital N to a vector of dimension capital N square. And by this row ordering, the vector that we get, let us represent this by the variable say U. So, by row ordering, the input image matrix is mapped to a vector say U. Similarly, by row ordering, the matrix coefficient matrix V is also represented by V. Now, once we do this, then these transformation equations can also be written as V is equal to a Kronecker product with a U. Okay. So, this Kronecker product of A and A can be represented as this A, and it is represented by A into U. Similarly, the inverse transformation can also be written as U is equal to A Kronecker product of A conjugate transpose, which is nothing but a conjugate transpose V, where this particular sign A this represents Kronecker product. And the matrix A, which is equal to the Kronecker product of the two matrices A and A, this is also an unitary matrix. So, once we do this, then you find that our two dimensional transformation, after doing this row ordering of the input image U and the coefficient matrix V, once they are represented as one dimensional vectors of dimension capital N square. So, this two dimensional image transformation is now represented in the form of in a one dimensional transformation form. So, by this what we have is, say any arbitrary one dimensional signal say x can now be represented as, say y can now be transformed as y equal to a x. And we say that this particular transformation is separable, where A is the transformation matrix. We say that this transformation is separable if this transformation matrix A can be represented by as the Kronecker product of two matrices A1 and A2. So, whenever this transformation matrix A is represented as Kronecker product of two matrices A1 and A2, then this particular transformation is separable, because in this case this transformation operation can be represented as y equal to A1 x into A2 transpose, where this y is the coefficient matrix and x is the input matrix. And we have mapped this y into a vector y by row ordering, and this matrix X is mapped into this vector X again by row ordering. Now, if we represent this in this form, then it can be shown that if both A1 and A2 are of dimension n by n, and then because this A is the Kronecker product of A1 and A2, this A will be of dimension n square. Okay. And by this matrix multiplication, again we can see this will be of dimension n square by n square. So, total n to the power 4 number of elements. So, the amount of computation that you have to do in this particular case will be again of order n to the power 4. And because this transformation A is separable, and this can be represented as Kronecker product of A1 and A2, and you find that this particular operation can now be obtained using n cube number of operations, order n cube number of operations. So, this again says that if a transformation matrix is represented as Kronecker product of two smaller matrices, then we can reduce the amount of computation. So, obviously, if both A1 and A2 can be further represented as Kronecker product of other unitary matrices, then it is possible that we can reduce the computation time further. And effectively, actually that is what is done in case of first transformations. So, today we have discussed about the separable transformation, and we have seen that how this separable transformation can be used to reduce the computational complexity. Now, some the answers to the quiz questions that we given in the last class. Obviously, in this case the first two are quite obvious. The third one, which we said that determine if the following set of vectors is orthogonal. Now, what you have to do is you have to check whether these vectors, these three vectors are pairwise orthogonal or not. That is, if you take the inner product of pair of these vectors, then only if you take the inner product of the vector with itself, you should get a non-zero value, and if you take the inner product of two different vectors, you should get a 0 value. And you find that if you verify on this, you will get the same result, that is A100 inner product with 100, that will be 1, but 100 one inner product with 010 or inner product with 001, that will be 0. And you can verify that obviously this particular set of vectors is orthogonal, and it is not only orthogonal, this particular set of vectors will be orthonormal. The fourth one, you have to find out the coefficient Cn. Obviously, this comes from the definition that if you integrate xt a n t dt over the interval capital T, then that gives you the value of this coefficient Cn. So, this again straightway comes from the lecture material that we have covered in our previous class, that is lecture number 11. Now, coming to today's quiz questions, the first question is, what is the advantage of separable transform? Second question, under what condition a transform is said to be separable? The third question, here we are given two matrices A and B. You have to find out the Kronecker product of the matrices A and B. The fourth one, here we have given two matrices. The first one is the transformation matrix A, and the second one is the input image matrix U. You have to calculate the transform this image matrix U when transformed with the transformation matrix A, and you also have to find out the corresponding basis images. Thank you.